Good afternoon, everyone. Looks like we have reached a pretty good quorum. Let me kick off the recording, and then we have a number of items on the agenda we'll do our best to get through. So welcome everyone to the May 12th SIGNODE meeting. We have a number of items. Just a reminder that meetings are recorded and later uploaded to YouTube for posterity and subsequent viewings. So please make sure to generally be kind and be all on our best behaviors. So with that brief intro, first topic today was advanced resource management experiences. Does the presenter, CAD, want to present?
Hey, it's me here. So let me try to share a screen. No, you need.
I'm going to have to make you co-host, Alex.
Yes.
All right, go ahead.
Do you see my screen now or not?
No, not.
Oh. It looks like I need to restart with Zoom because of privacy on my Mac. Give me 1 second. I will rejoin in a second.
So maybe in the interest of time, we can do the bottom up, the agenda while Alex is getting back. Victor or Jay, do you want to give an update on how the testing kickoff went?
Yeah, I will. Jay is not able to attend today, but yeah, we had the test kickoff. It was we had great attendance. I don't know. I think there was like 25 folks there or so. And for the first meeting, it was pretty much introduction to the test grid, end-to-end node test. Some of the folks were just new and not familiar with that, and so we spent the majority of the time there. And then we looked at the spreadsheet and talked about sort of how to correlate a test with the test code and where the job is defined. And Dims was there, and he gave us a great overview. And I just want to give him a big shout out and say thank you for attending. Thank you for sharing. That was really good. That's just the heart of open source, and I really appreciate that. And I'm sure others on the call did too. So thank you, Dims, for that. I shared the recording, so we did record the meeting for folks that were not able to attend. And so the next thing we're going to do is complete the spreadsheet, which has a list of all the tests. There's a little feedback, maybe do a little cleanup, and then volunteers can sign up for the test to investigate. And there's already some that have signed up, and I want to say thanks for that. I appreciate that. And I think that's it, unless there's some comments or questions. Oh, we will have a weekly meeting, and right now it's set up for Monday at 1 Eastern Daylight Time. I said until we get this under control, until we get it in a stable state where it's mainly green, and so that's the goal.
Awesome. Well, that sounds great. Big thank you again, Victor and Jay and Dims for helping out. Alex, are you able to present again?
Yes, make me co-host. Can you make me a co-host? Okay. So this one. So do you see my screen?
Yes.
Good. All right. So colleagues. My name is Alexander Konevsky. I work for Intel, and in past year or so, me and engineers from our team we were trying to do some different proof of concept work for our customers, all related to hardware resource management. And when we recently saw some of the discussions regarding the topology manager, and especially like with memory manager, we realized that what not all the work what we were doing is widely known, or like some of the experiences what we had is actually might be useful for ours, because we have a bit range of use cases. So the way what I want to talk today is what I will show some demo, and then I will talk about like specifics of hardware, like specifically it's like CPU memory, what we know about currently, and what already like some on the water stones what we already stepped on. So probably like when we are designing some new things, we can try to avoid that. And the last part is about the user experiences. Again, something what we tried and something what we think might be better. So first of all, the demo. It's a recorded screencast. It's about 10 minutes long. It's a stock Kubernetes, like nothing modified, stock containerd, nothing modified, plus few components added in between. The demo will be focused mostly on CPU and memory, but we also can do some things related to block I/O, to cache management, and memory bandwidth, and a few other like smaller things. So let's start with the demo. The demo is going to be showing like one single node cluster. The machine is actually the standard Dell server, like 2 sockets, Intel CPU, many cores. A few things which is a bit tricky in this machine is what it enables the configuration of memory latency specifics, and plus it also had memory which is so-called like persistent memory or Intel DC memory, which like allows you to have a lot more memory and cheaper than DRAM. So by default, let's look what's happening if you try to run application. Like we have one pod, multiple containers, each of those like burstable and running very simple application. And this simple application will be just reporting where exactly it actually runs. So like which memory nodes are enabled, which CPU pools are enabled, where it's located, like socket and so on. So the first container, we can see what it's located on DRAM node 0. We have shared pool of CPUs, and you can see what it shows what it's on CPU socket 0 and NUMA node 0. The second container, NUMA node 2, again, different set of shared pools of CPUs, still the same physical socket like socket 0, but on different NUMA node in terms of memory. The third container spread it to the next socket. Again, separates pool of shared CPUs, separate memory nodes. And the fourth container, again, in second socket, another memory node, another set of shared CPUs. So you might ask, like, okay, so we have containers which will fit in this small shared pool of CPUs, like part of the system. What happens if I have a workload which actually tries to use something more than that? So how this is going to be placed? And for that, we have a second part. Let it delete. So now I think what a workload which doesn't fit in one part of the system. So as you can see, I have in each NUMA node 28 cores, and now the workload requests like 29 cores. and report created. And now you can notice what it has for both memory from NUMA node 0 and 2. CPU shared pool combines with both things, but it's still within one single socket. So like the memory is close enough, the workload optimization is such what like it still gets the best of the memory bandwidth, best of the memory latencies. So the next thing is what, like the scenarios what we discussed. So what happens if I have a workloads which actually wants to run together? So for example, like using the shared memory. So we tried to experiment with something and we come up with the mechanism to do like affinity and anti-affinity. So you can look, you might notice like in metadata, we have annotation which actually says like the container 1 and container 3 should be close together. And container 1, container 2, and container 2 and container 3 should be as much as possible separated. So for example, like the logger, which potentially might be not that as important for you, you will try to move it away from the data plane of your application. So now it's running. And let's see what it will report. So container 1, node 0, socket 0. Container 2, it will be balanced out still within same socket, but on another memory region, another subset of cores. And container 3, it has the affinity towards container 1, so it landed also to the same shared pool, the same as container 1. So socket 0, NUMA node 0 in terms of memory. And container 4, it doesn't have any preferences, so the system balanced it out to another socket just to spread the loads between the, all parts of the system. All right. So the next thing is actually, so this is like the CPU and memory resources where we can optimize. The next thing will be about the devices. So right now, the topology manager is only capable of aligning the resources when you have explicitly requesting some of the devices. What we tried and what we implemented is actually the possibility to detect if container is using something. So in this YAML example, where container 3 is using the volume, which is actually located on the local physical disk. So we know what it's like. It's local storage, it's some PCI device behind it or NVMe device behind it. So we can try to place it close so to avoid the data transfer between the different parts of the system, just to improve performance of the disk operations. And this is practically like we can detect what kind of PCI devices it's located to. We can detect which cores are close to it, and when it means the container will be placed again close to those. And this is actually working across different devices. So we tried it with storage, we tried it with NFS shares, so we can detect if it's connected to some network. And obviously, if your container is using some of the device, expose it via device plugin. So any device node, if we can detect topology of a device from Linux kernel, when we do same. So here's the container 3. As I said, this is the device which which is close to NUMA 0, so the container free landed on this area. And the last part of the demo, it will be something what is not very well, not very common yet in the system or in the world, but something what soon will be available to the big data centers. So practically, we call it, this thing is memory tiering. So it's the scenario when you have in the same system different types of memory. So as I mentioned, like we have DRAM, we have a bit slower persistent memory and use it in volatile mode. And we have a container which will be utilizing both of those. So here you can define what container 1 is performance critical, so use only DRAM. Container 2 is something like logger, which can be slower, and container 3 is just a normal workload, which can do balancing of all of those. So here's what we expose with downwards API. So for container 1, critical ones, we say CPU cores, but memory, only one is allowed, only DRAM node is allowed for this container. Here's with a bit slower memory. So shared set of CPUs, only one node enabled, and only PMM-based node is available for workload. And here is container free. So standard workload, both memory types are allowed. You have DRAM, you have some PMM, and the same shared set of CPUs. And practically, like this is not limited only to PMM. We also able to detect high bandwidth memory and do exactly the same thing. So if you have some specific network workload, which is really sensitive on the bandwidth or latency of the memory, you most probably want to use the high bandwidth memory, and when set your application would use the CPUs from closest region from this memory type. So that's end of the demo. Now I want to talk about like how we actually playing with all of this Tetris, with all our containers and with all of those resources. So if someone seen previously some of my presentation, what I was previously doing, you've probably seen this picture, what I love to show. So this is the thing what people are thinking about how hardware is actually looking like. So you have like two sockets, you have memory controls, you have some devices attached. And when people are talking about the NUMA nodes, we assume what like one socket equal to one NUMA node and trying to use it as a synonyms. The thing is what this picture was accurate maybe about 15 years ago. But actually, even about like 10 years ago, this picture became obsolete. So the current generation of the hardware, what people are using nowadays in the data center, is actually a bit more complex. So we have still like multiple physical packages of CPUs. We have one or more dies or chips inside these physical packages. And when those chips contains multiple cores, and many of those cores actually not equal. Like some might be running faster, some might be slower, some might have a turbo frequencies, some might be located a bit closer to some other interconnects, and so on. And you might have interconnects between those physical packages, and topology of those interconnects, it really depends on the vendor, on the type of a motherboard, it BIOS settings, and many other things. And when we are talking about memory, Actually, modern CPUs, they usually have more than one memory controller, and each of memory controller have multiple channels. So when we are talking about the NUMA node, what Linux kernel says, it might be working in different variants. So one variant is what, like the standard or most commonly used, is what when the two controllers are working in the same, like in the parallel. So it's a bit more bandwidth, but also a bit bigger latency. And if you switch on the BIOS setting, so you get less latency, but you have instead the two NUMA nodes visible in the Linux kernel. And as soon as you start to add more different memory types, you, like Linux kernel, will start to see an additional NUMA nodes, which actually doesn't have the CPU cores. So when you're planning to use the NUMA node for something, you need actually to think about like how it actually represents and how it's actually connected. And when we have devices, so even though Linux kernel reports it attached to some NUMA node, in reality, each PCI devices, we actually have a locality to some PCI cores because the PCI controllers are somewhere close to one core rather than to another. And then we have a bit more complicated for the devices, like the inter-device connections, the devices which can be connected in our means rather than PCI. So you might want to detect more additional hardware things, but it's out of scope for today. And the thing what I also mentioned is what, like, beside the devices what is covered by accelerators, you usually have a bunch of the devices was just integrated in your motherboard. So all kind of I/O, all kind of embedded chipset features, all kind of network interfaces, and so on. So when you're thinking about like how your workload is actually needs to be optimized for hardware things, you need to think about all of those interconnects between the devices, and that's easily become like vendor specific, unfortunately. So what we learned when we tried to manage the CPU-based resources. So first of all, as I mentioned, the CPU is a bit complex thing. Even though the Kubernetes right now does a lot of simplification about the cores with threads, all CPUs are equal. In reality, it's a bit it's not. Even though we have different usage of CPUs, so like shared with exclusive, which is possible with current CPU manager. But when even for exclusive usage, there is an interest in different high-performance workloads to utilize the isolated one. So isolated is the one which Linux kernel is not automatically schedules the task. So the workload needs to be specifically pinned to be utilizing those. So of course we can try to introduce new resources for that, but it doesn't really make a lot of sense. So it will complicate the user experience for the things. So in the policy, what I showed, unfortunately, it was not part of the demo, but I would say if a container would be requesting the CPU, like the full physical CPU, and we have in the system detected what there are isolated CPUs from Linux kernel, we would give to this guaranteed container the exclusively isolated CPU. Again, transparently for current Kubernetes implementation. But beside that, so with CPU, what we know, it's like just shared time, like differently used, but it's still like the one big shared time. Where CPU actually have a bit more resources. So we have cache control and we have a memory bandwidth. And those things, it's not something, so it's harder to represent it with a current resource model. So, for example, like the memory bandwidth, you can say, what for my workload, I want to limit it for 50% of memory bandwidth. So it's not exclusive allocation. It's not. It's kind of like gauge type of resource, which is elastic, and it depends also on the memory controller. So you have, if you have multiple, you need to specify the with limits on multiple controllers. So again, if we want to introduce it to the users, it might be challenges how we actually want to represent it for the UX. So next thing, the interconnect. As I mentioned, it's vendor and hardware dependent, like how many interconnects you have, how much traffic you have on those. And when people are referring what, like I have a NUMA problem, and because of that I have a performance, and it usually means what your interconnect between the CPUs is busy between for moving data between the memory controllers and actual CPU core which processes this thing. And that leads to the thing is what, again, misconception is what NUMA is related to the CPU. So NUMA is really memory, and different vendors represent, they have a different meaning of a NUMA, and this is really configurable via BIOS settings. So in Intel it's called SNC, in AMD processor it's called like NPS nodes per socket, and it can be like 1 to 4 in different configurations. But again, it's something what you need to take in mind if you try to start exposing these things to the users. So the good thing about the CPU actually is what the workload, if you want to migrate it from one set of CPUs to another CPU cores, the cost of this migration is actually quite low. One underwater stone is what actually we used to say what like kubelet is having a CPU manager, and kubelet are actually dictating of how CPUs are assigned to workload. The problem is what it works fine for normal workloads, normal runtimes like runC and so on. But as soon as we start to have complexity of VM-based runtimes, so the meaning of a CPU number might not be the same inside and outside of VM. So
it's okay, Alex. I mean, that last point is important on if you're running Cube on virtualized infrastructure versus just Metal itself, right?
It's a bit less important. So it depends on how your hypervisor in undercloud actually exposing the information to the kubelet. So, for example, I saw some presentation about VMware Tanzu thing, and they implemented actually very good scenarios. When the virtual node, or well, dynamic node is provisioned, they create the node which hypervisor actually put nicely inside some memory and CPU domain. So you get the automatic optimization of the topology. But it's like it's done by a VMware hypervisor for you.
Yes, we and also Google GCE also have the similar things. We have like the optimized VM for customer, and to benefit from the optimized of the NUMA and the CPU and the memory and the needs of the host, and for that particular VM. So a lot of those detail is hide inside like the hypervisor implementation. So I just want to share here.
Yeah, and actually, the whole reason why I'm talking about here is, and actually the reason why I show it with demo is what, like, the user experience is important. Back in November after KubeCon, I spoke with Tim Hawkin, and he mentioned also this scenario is what, like, Google Cloud philosophy, what we used in when create Kubernetes was like to hide this complexity from the user, and that's why we're also trying to use the same principles. So looking at CPU resources based on all this, what I wrote here. So this is how we actually look at the topology of the things. So we can detect, would it be like bare metal or would it be cloud hypervisor which expose it? But from Linux kernel, what we can find out is what, like, the socket number, like the physical package ID. We can find how many CPU dice or chips present in one physical package. And when we have group of cores which is close together within one die within some socket. So for us, what we actually do is we creating this kind of virtual tree of resources. So we like virtually splitting the whole node into multiple zones. And for each group, so like each of these leaf nodes, we have group of CPUs, we have group of memory, and workload actually end up in this group. So inside this group, we have similar to what currently have like the CPU manager. We have shared pool and we have exclusive allocation if workload requires an exclusive thing. But what we also able to do is we can create dynamic pools. So for example, like isolated CPU or special case with throttled. So for example, if you run AVX 512 heavy instruction and it start to throttle CPU cores to do this big vector operations. So to not affect our workloads, we creating this throttled pool for AVX workload, and the rest of the workloads is moving out of this shared pool. So we are not affected by this scale down of frequencies. And what happens if we cannot fit in this small group? So it's easy. We just go one level up. So this helps us to actually eliminate the scenarios what we are trying to, we get to the situation what we cannot fit and we cannot reject. So we need to reject the pool. And all this tree structure what we are having is actually really dynamically based. So for example, if we detect what we have in the system, you have only one die per socket. So the whole this layer of the dice will be missing. So the tree will be like not that deep. And of course, like if you have only one socket system, again, like the socket layer will go out and you will just have a similar group what you have currently in CPU manager. So that's CPU. And as soon as we start adding the memory in the picture, it becomes a bit more complicated. So as I mentioned, we have, like most people know right now, you have only DRAM. Nice, good thing. But in the market, in the current hardware architectures, there are two other types of memory, which is also present in some of the scenarios. So one is persistent memory, which is used in volatile system mode. So I call it PMEM in this presentation. And another is high bandwidth memory. So like high bandwidth is usually like several times faster. But again, it's seen in the Linux kernel as NUMA node without any CPU cores attached to it. When you have two types of memory inside the Linux kernel. So one is normal, like your normal DRAM, and second is movable. And we think which is interesting in the movable part is what, like, you cannot, like the movable, the kernel will not allocate any special pages inside the movable. So if you try to run any workload and only allow to allocate memory from movable node, you will end up in the trouble. So kernel will not be able to run it because it simply cannot load the shared libraries into it. So if you have a system where like some of your memory represented as movable, you need always to select the workload which says like one normal DRAM memory plus this movable, and the workload then should be able to distinguish between those and then do balancing inside your user space application. And that leads to actually the problem of the NUMA. So when we are talking about the NUMA and specifically memory part of it, so we need to understand what kind of memory it is. Like, is it normal? Is it movable? How it's connected? Does it have CPU or not? Is it like, even if it doesn't have the CPUs, what actually the closest NUMA node with a CPU? So you can define for your workload how it should be placed. And when you have a distances, it can help you. It can give you a hint how it's connected, but you cannot trust those distance numbers for any performance valuation, because like many BIOS, many server vendors, they have like just a hard-coded like random numbers on those distances. So they relative to give you idea how it's connected, but it's not about how it's actually how performant it is. And based on all of this, so if you have a workload and you want to migrate it between like one region to another. If you do it within one physical like chip or one physical package, usually it's relatively well, it's costly operation, but it's doable. But as soon as you start to cross the inter-socket communication to move the pages between them, it's become really really high load for the system. So kernel will lock your application, you will get latencies, you will get interruptions on your workload. So try to avoid those.
So Alex, just a time check.
Yeah,
we're
I
over.
have 4 more slides.
Okay.
Right. So related to it, so the modification as soon as we added memory in the picture. So what we can detect how topology is topology of the system is located. We can detect how the memory and IO controllers are located, and when we can locate where the CPUs, DRAM, and PMEM and HBMEM are located. So practically, like even though if it's represented as a different NUMA nodes, we group them into the same pool, and when we allow the workload to actually specify what kind of memory it will be able to use. So by default, we allow both DRAM and PMEM, and the reason for that is actually the way how it's implemented in Linux kernel. So if you have this scenario where multiple NUMA nodes are enabled for workload, and some of them is DRAM and some of them is PMEM, is what kernel will start to do similar to autonomous scenario. But instead of like locality of CPU, it will start to analyze how cold or hot your data is. So the colder your data is, the less used or read-only usage, it will be migrated in the background to a persistent memory, and like more actively use it in the DRAM. So again, kernel helps to optimize the performance of your application. All right, almost end. So the user control and UX, as I mentioned a bit earlier, so we really want to have something what is suitable for public clouds, for VMs, for bare metals, and so on, and especially for all non-trivial resources. And again, with good user experience. And if you start to track all of those and you start to place in your workloads, like sooner or later you end up in a situation like, okay, can I fit it into the node? And we have like 2 scenarios. Like one scenario is rejecting. That's practically the only thing what is possible currently in the topology manager, because all the placement done inside the admission loop. And second thing is rebalancing, meaning what, okay, we got something new, but can we adjust something in the runtime to fit? So the famous the story of a jar and different sizes of the rocks. So if you put it in wrong order, you end up with a problem that you need to reject. But if you start reshuffling them, you might able to fit more. And based on this reshuffling and rebalancing what we had, we figured out. So like there are, as I said, like assigned devices is something what you definitely cannot move. So if you end up in the situation what you have only assigned devices to your workloads and you cannot move, so you get back to the reject state. But if you have also about other resources like memory and like less priority, for example, like burstable or best effort containers, those are sand which you can easily shuffle between different buckets in your system. So why at all I'm talking about all of this? So UX, mostly UX. So the scenario when we are trying to expose all this NUMA awareness to end user, I think it's not a great. So what user expects by default, it presses the button, like put it, and it runs the things. When some of the patterns, what we're seeing. So instead of defining like I want this amount of memory from NUMA node 0 and another set of amount of memory 0, we see a more nice pattern of affinity and anti-affinity, saying like this container is interested to work together with this one, or keep it away from this one to not affect our workloads. The same goes with device pipeline. So right now, the topology manager is talking about, okay, how the device is connected to the system. But for us, in many scenarios, we're interested to have a device pipeline. So for example, like GPU connected to FPGA, connected to some network card, which is connected to specific network, and so on. So it's less about how it's connected to CPU. It's more how it's connected to out-of-bound services. And of course, the future. So we shouldn't be doing something today, which we know what it will be obsoleted by the hardware, how hardware is evolving in the future. And the main thing is, what do we really want to have all this complexity in kubelet? Especially like if we have nowadays a lot of VM-based runtimes, if we have like hypervisor like VMware, Tanzu, and so on. So maybe we need to think what part should be done in kubelet and what part should be done in the runtimes, so we can enable again the competitiveness between runtimes and get it more pluggable, get it more advanced, I would say, based on the actual use case. So you can have a generic kubelet for whole cloud, and where you have like resource-specific needs when your runtime will be handling it. All right, so that's what I wanted to show. I have another slide, but I don't have time for it actually, how it's implemented.
So I guess, Alex, first a big thank you for the detail. What I'm wondering is, in your demonstration, you showed a stock cube and stock container runtime, and then alluded to add-ons, but didn't enumerate those. It seems like, have you developed a set of add-ons that have done what you felt like should be done next? And is that something you want folks in the community to review? Like, I'm trying to think, like right now, I can't tell if the parting message from your presentation is.
Okay, well, let me show one more slide. So we actually think what I demonstrated how the demo is done. It's done by our proof of concept project. We call it CRI Resource Manager. So we used it for prototyping all of these additional things. So how it works? It's just a proxy between the kubelet and actual container runtime. So what we do, we get all the CRI messages, and we injecting and managing our own idea how system is like handling the resources. And based on that, we are able to do like CPU, memory, cache, like RDT, memory bandwidth, block IO, and this dynamic pooling or dynamic handling of AVX throttled cores. So the thing is, we implemented it, but the main point of implementation of it, and the main point why I showed all this like tree structure, is what we probably want to revisit how we actually thinking about the native resources in the system. So we can do both ways. We can try to make the kubelet more hardware aware, or we can do the opposite. The kubelet will be a bit less hardware aware, but the container runtime itself will be trusted more on actually on the allocation of the hardware resources. But when we need to enhance the CRI messages, actually to expose what container actually wanted. So like real memory requirements, not only limit. The same with CPUs, the same with huge pages, and so on. So for container runtime, in similar to like what virtual kubelet is doing, is what like container runtime should tell. I can do that. And kubelet should tell to it, saying like, this is the container, run it the best you can.
Awesome. Well, go ahead, Dawn.
Go ahead. Go ahead, David.
Yeah, I was going to say, I feel like each week we're getting pulled to explore a different tension, and all designs require a sacrifice along some dimension. So I think as a broader community and a set of users you're looking to support, like it's inherent you have to make a sacrifice that uh, upsets some balance in the system. And I think what you presented here is really cool to see. I would say that probably the sacrifice that it doubles down on is the cluster-wide scheduler not being node local aware. And I could see how for many folks that is perfectly reasonable. And then I could see how some others wouldn't appreciate that sacrifice. So I guess in closing, like one, I know Victor was looking to set up a more recurring discussion on this topology aware problem so we can get all these ideas out. And so Alex, a big thank you for presenting this now. I think in that forum, it would be good to talk through like what the design sacrifices are that are made. And personally, I feel better if we can keep the kubelet in a space that doesn't make it have to be the actor that makes that sacrifice. And so maybe that your presentation today is one that I'll have to reflect on and think through. But I appreciate the deep detail.
One
Victor?
of the reason why I showed this speaking part of the demo, and so the thing what we tried to do is what the scheduler knows about the total amount of resources. And for us, when we splitting the system, sorry, am I me? Do you hear me?
Yeah, we can hear
We
you.
can.
Yeah. So
There's
somehow-
echo whenever Dawn turns on her microphone.
Oh, I just try to respond. We can hear him.
Now we can't hear anybody. Yeah, I was trying to control the echo. I apologize. Alex, can you?
Yeah.
unmute?
So what I was trying to say, even with splitting the system into multiple smaller buckets, if we cannot fit into this small bucket, we can bubble up to upper layer. And on the upper layer, because it's just like summary of available resources, it will exactly match what scheduler thinks about the node. So we end up with like less amount of rejections from the node for the container. Well, the only way, or the only scenario when we got a rejection is the scenario when the container have a very strict by annotation set with criteria. So like align me on top of a device, align me containers, and we simply cannot fit it even if we do rebalance, for existing workloads. So again, UX matters, and we are trying to make sure what stock Kubernetes, what stock user experience is hiding all this complexity.
Awesome. Well, thanks again, Alex. Victor, do you want to take a moment to maybe put a bow on this topic and draw attention to what you were trying to schedule?
Yeah, sure. Thank you, Derek. Alex, that was a great presentation. I think, I learned a lot on that too. Very, very good. So what Derek is referring to is, there's an effort to get everyone together for topology aware discussion. We have been doing this Topology Manager for several months now, but primarily it was focused on getting to beta. So now once we're out of that, we're looking at NUMA-aware scheduling. Just like this meeting, it takes a very long time to present for people to absorb. And so the idea is we would have a separate meeting to focus on this. What I would propose is that we, first we've got created a channel, topology aware scheduling. And these are in the SIG node meeting minutes. But we propose having a meeting on Thursdays, 9 a.m. Eastern Daylight Time. And I know that won't work for everyone. And if we need to, we can do a survey and try to find a time. But up until this point, it's been some folks from Samsung, Chris and BG and NVIDIA and Intel looking at some of the previous proposals, and I think this fits right in. So yeah, that's what we want to do, take it sort of to a different meeting to where we have time to dedicate and not consume all of SIG node. And then once we get a consensus, we can bring back and sort of highlight to Signode and share with other folks. So I think that's the plan and proposal. And any feedback or comments on that?
Yeah, it was already like for a long time discussion about like let's bring the work group resource management for this topic specifically. But as Derek said a couple of weeks ago, we can do it less formal. And yes, I am also from Intel, and we are working closer to colleagues like Connor, Nolan, like Swati in the past. So we're all in the same team. We're just looking from different perspective on the same problems, and like some things more advanced and some things more simple use cases.
Cool. Well, I think it would help us to at least try something for a few weeks to get an opportunity for people to get all of their ideas out at a higher velocity than maybe the weekly meeting is allowing. And hopefully those who are interested can join. We have about 10 minutes remaining. Trying to look through the topics that stand out. I wanted to know if Joe or Mrinal wanted to talk about maybe their experiences with
Sure.
Postgres. It's not a regular participant, but it was a really interesting write-up as well.
Yeah, so mainly wanted to just get Joe's item on the agenda. So we had a call with him. So, Joe, are you able to talk about Postgres issues?
Well, I don't know to what degree you want me to go into details. We probably don't have time for a lot in 8 minutes. I can say that I've been down a very, very deep rabbit hole over the last 3 or 4 weeks when it comes to the combination of Postgres with Kubernetes and the Linux kernel and out of memory killer and all of that. Postgres, because it has very high guarantees when it comes to durability and correctness and availability all at the same time, I actually found, you see in that write-up I did, there's a footnote, the original mailing list discussion about the Linux kernel OOM killer, describing it basically as a bug in Linux kernel. So that's kind of, that summarizes the way the Postgres community has felt about that facility for many years. It's been 17 years. The community has long had guidance for bare metal, at least in VMs, on how to avoid having Postgres get killed by the OOM killer, which, in a nutshell, are change overcommit so it doesn't happen, and tune the OOM score adjust so that the main parent postmaster process is scored at -1,000 and that the children are scored specifically at 0 for the adjust value. Currently, that's not possible under Kubernetes. And furthermore, although many of our customers like the idea of running guaranteed pods, the downside of running a guaranteed pod is that because there is a memory limit, if you exceed that memory limit, the OOM killer is what enforces it. And that has a number of bad effects on Postgres, which I also outlined. Does that kind of summarize it, Mrinal?
Yeah. So, Derek, I think we may benefit from having a longer slot maybe next week if possible. And meanwhile, we can take a look at the issue.
Yeah, I wanted
to just quickly add one thing. The original reason, QoS, we are not using the OOM score disabled, OOM killed disabled, like the -1,000. It is because if you specify, especially the database type of the workload, if you are using those kind of things, and you end up the kernel maybe couldn't kill anything reclaim memory, then you could end up have the whole node crash, and the end up have database could have the corrupted data. That's even more dangerous. I just want to share here, and so this is the lesson we learned in the kernel before. But of course, the new kernel, I know they reserve the more memory, And earlier, like Alex also mentioned something like the hand touch a base a little bit, but not really. So they reserve more memory for those kind of things. So this you could kill. So we have the experience before, like even kernel thread and reclaimer thread cannot run. And to decide it to which container to kill. So the all can do is just crash whole the machine. So that's the background why we learn a license never really using neglective one sovereign here. I just show some background.
Yeah, I guess.
Hi, Don. This is Vinay. I think we touched upon this earlier in our prototype where we experimented with enabling kill disable for specific pods via annotations. And if we combine this with vertical scaling, I think there might be a solution where the application is paused just until the resizer can determine you need more and you can get more. Instead of killing the pod, it goes into a pause state until VPA, for example, is able to resize.
So there's a new way to do because the new kernel and a lot of things we could open discussing. But I just want to say like the different kernel version may have the different behavior. This is back to like the earlier Alex presentation, and it's not like the single solution can satisfy all the use cases.
Yeah, that's probably true. But let me just add one little bit of information about this, and that is that unlike a lot of workloads, something like Postgres, a user by writing a bad query or by specifically writing a query that needs a lot of memory can, if you allow arbitrary SQL, can consume a lot of memory. So it's not like the workload can be guaranteed to be within a certain set of limits very easily, unless you only run a well-written application against it, and then you've benchmarked it and you know how much memory it needs. There's really no way to prevent the memory usage from going up. So, Postgres, I think, is a little bit, unique in that regard compared to a lot of typical containerized applications. But I also think that persistent, database type workloads are becoming more and more common. The other thing I want to mention, though, is with respect to that, one of the things that, and I've been playing with this for the last week or so, basically user space OOM memory management for Postgres. Postgres has also had for a long time the ability to signal a process that's out of control with a SIGINT, and that will cancel the query. And so Postgres can very gracefully recover from a badly written query that is driving memory by simply sending a SIGINT to that process. So that's also different than a lot of workloads where you're better off just killing the container and spinning up a new one. In Postgres's case, you don't really want to do that. You really would rather either do a SIGINT or, worst case, a SIGTERM. In either of those cases, you'll quell the memory usage, and you will not have any negative effects on your Postgres installation. Whereas if you get SIG-kill, it has all these bad effects that I was talking about.
So first, for those who can stay on 2 or 3 minutes extra, I wanted to just ask one other question, if that's okay. So I've seen the similar feedback for other applications that encounter this problem, particularly like in analytics spaces, and especially where they're running multiple processes within a container. The one thing I was curious about was, do you feel that running more than one instance of Postgres per host is something that you would recommend or not recommend? Like when you set the score adjust all the way down to -1000, it basically feels like you're assuming total ownership of that host. So I guess what I'm curious around is the Postgres community, for any operators they might be building or Helm charts they're authoring, orienting towards keeping instances of Postgres separated among each other?
So there's a couple of pieces there I think are worth addressing. One, the ohm score adjust of -1,000 only applies to the postmaster, which is really just a listener. It doesn't use much memory. And part of the reason for that is it's orchestrating all of the other processes. The other processes we normally have an score adjust of 0, which allows them to actually have an OM score. And that's so that the runaway, and the other thing that maybe I didn't say, but I should have, is that Postgres is multi-process architecture. So every time a client connects, there is another process that's spawned by the postmaster. Postmaster just basically grabs the incoming connection to a socket and forks a child process. The child process does all the work. So, and if you've got, in a typical scenario, you've got 200 or 300 maximum connections, you might have 300 Postgres processes running inside that one container. Each one handling a different client backend. But as I said, only the postmaster is scored at -1,000. The rest of those child processes are all at 0 for score adjust. The other thing I will say is our experience at the company I work for, we have a Postgres operator that is actually, I think, probably the furthest along of any of the ones that are out there. We have many customers that are running, in some cases, thousands of instances of Postgres in containers on Kubernetes already. We haven't seen a widespread problem, but we have had people complain about things getting, OOM killed in the field, because it does happen. It tends to happen when they've severely undersized their container. And in a lot of cases, they're doing that because they're doing testing. So it hasn't been a huge problem in production, but as more and more people use Postgres, it become a bigger problem. But that all said, they do run multiple Postgres instances on them.
I think that even without run multiple PostScript on the single node, you will have problem, because your master have that set disable, neglected one sovereign, and all your children process will inherit that by default. So
Postgres has got C code in the startup that looks for 2 environment variables that, if they're defined, will reset.
Okay.
Yes, and that's what the typical guidance is if you use the systemd or something.
Sure. Got it.
And I've tested that; it works fine.
Okay.
It works fine with a guaranteed pod, because with a burstable pod, you're already above 0, so you can't reset it down. You can only reset it up.
Okay, so we can carry on this discussion, but I have to leave. Thank you. Sorry.
Oh, sorry. Could I have?
Yeah, go ahead.
No, just because we are running out of time, and we are going to present presentation on Memory Manager today. And can we just ask about review of the CAP, because we can present the presentation next week, but
Yeah, I think if it's okay, maybe we could review the CAP or the presentation in the first meeting that Victor was proposing. I feel like, and so if that happens this Thursday, like maybe we can do something faster than next week for you, if that's okay.
Okay, so yeah, so okay, thanks for that.
Okay. Again, I apologize that we had a lot of topics on today's agenda, and so we're trying to get more bandwidth to have time to discuss complicated topics. For the crunchy topic, I think if it's okay, I'd like to do a deeper dive on it next week to see like what we could do and maybe what that model may or may not look like. And thanks again for joining today and sharing your experience.
I appreciate it, but I would ask if we could do it the week after next, because I'm not going to be available next week.
Sure. Yeah, I guess it just gives us time to think through it. The only other thing I feel like earlier iterations of Cube also set score adjust differently based on pod priority. And so I was just curious if that was something that folks had maybe wanted to reflect on, and we can discuss on that in 2 weeks if that's fine.
Great, thanks.
Otherwise, thanks again for a very productive session, and we will be in touch.
Thank you.
Thanks. Bye.